Am I audible?
Yes, ma'am, you're audible now.
Okay, can anyone recollect what we did in the last class? So we, yeah, yes,
A
sir.
representation, evolution, and optimization.
Yeah, we learned different steps of learning.
Learning process, yeah.
So in that we learned representation, evaluation, and optimization. And also we learned the two process of learning, which is deduction and induction. And what else we did?
Classifiers. Spoke about
Yeah. So we learned different types of classifiers. One is parametric classifier, and the other type is non-parametric classifier. So what is parametric and non-parametric here?
Ma'am, parametric follows specific distribution, whereas non-parametric does not assume a fixed distribution.
Fantastic. And regarding the learning?
Ma'am, parametric learns from finite set, whereas non-parametric directly learns from the data.
Fantastic. So the first thing is about assumption. The parametric classifiers has a strong assumption. Non-parametric classifier has a minimal assumption of the data. Parametric classifiers learns from the parameter, whereas non-parametric classifier learns directly from the data. So we can say the parametric classifier is highly flexible. It has an adaptive boundary. But parametric classifier works well with larger data. Non-parametric classifier works well with smaller or complex data set. So we also saw some examples for parametric and non-parametric. So in today's class, what we will do is that we will see the examples with little more information. So let's start with non-parametric classifier. So what is a non-parametric classifier? It has no or minimal assumptions. It grows with the data. It learns from the data directly. Learns directly from the data. So examples are KNN, SVM, decision trees. So today we will see all these three. So let's start with KNN. KNN stands for K nearest neighbors. So KNN is a non-parametric classifier. Here K is a integer. It can be 1 or greater than 1. K can take the value of 1 or greater than 1. K is a hyperparameter. Because we set the value of K before the algorithm runs. So we are setting the value for the parameter. So it is called as an hyperparameter and it used to control the algorithm. So previously we studied what is meant by K-means algorithm or K-means clustering. So K-means clustering uses unlabeled data. So it is an unsupervised algorithm. Whereas KNN works with labeled data. It uses supervised learning. So that is the difference between k-means algorithm and KNN. Since it both starts with K, you shouldn't get confused. One is an unsupervised algorithm. The other one is a supervised algorithm. So generally KNN is fast to train because it saves the copy of every incoming sample into the database. The interesting things happen when the training is complete, when the new sample comes, how it is going to characterize is really an interesting thing to know. So let us assume an example. Where you have classes, namely square class, triangle classes, and a circle class. So now you have a new data, which is a star, which is coming here. So now what you will do, so you will see, so if K is going to be 1, then what you will do is that you will look for the nearest neighbor of this star. So the nearest neighbor of this one is the circle. So the class of the star will be circle. Supposing if K is going to be 9. So then what you will do, you will collect 9 samples across the star. So the 9 samples can be 3 circles, 4 squares, and 2 triangles. So these are the 9 classes which are closest to these are the 9 samples which are closest to the star. So if you look at, we have 3 circle elements. We have 4 squares and we have 2 triangles. So we have the largest number of vote for the square. So the class of the star is square. When K is equal to 9. When K is equal to 1, the nearest neighbor was a circle. We looked for only one nearest neighbor because the K is showing the value as 1. We looked for only one nearest neighbor and it was a circle. So the class of the star was circle. When K is equal to 9, we looked for 9 neighbors which are close to the star, and each of them are we had 3 circles, 4 squares, and 2 triangles. So since the square had the largest number of entry, the class of the star has been assigned as a square. To sum up this, we can say that KNN accepts a new sample to evaluate and so that we find the number of votes. That category will become the category of the new sample. Is it clear? So if you look at KNN, it does not create any explicit boundaries. Like usually a classifier means it will create boundaries, but here it is not creating any boundaries. It is only finding the nearest neighbors and then attaching a class based on the maximum number of votes. So it does not create explicit boundaries. So there is no notion of creating a region or a area that sample belongs to. So KNN is usually attractive because it is exceptionally fast. But what is the problem is that it consumes a lot of memory. Why it consumes a lot of memory is that because it has to save all the input samples. When you look at here, all the previous input samples are saved. Then only we can find the nearest neighbor. So in the search of nearest neighbor, what happens when it consumes larger memory? It slows down the algorithm and the algorithm becomes very slow. There are ways to speed up this algorithm, but however, when we use some real life applications, we may not be able to apply this KNN for real time applications. So, for example, self-driving cars or any medical emergency detection systems, we cannot apply this one. Even for web-based systems, for recommendation systems, which needs instant results, we cannot use these application. We cannot use this algorithm because it needs a lot of neighbors for searching and it needs a lot of training data. So that is also one more problem of KNS. Suppose if you have lot of features, if lot of features are there, then KNN will succumb to the curse of dimensionality. So as the dimensionality of the space goes up, and if you don't simultaneously increase the number of training samples, what happens? The number of local neighborhood will reduce, or else it needs to find a farther, it has to search farther for the local neighborhood. So it can make it harder for the KNN to get a good collection of nearby points. Thereby, this case of dimensionality, I will affect the KNN if it has larger number of features, provided it does not have enough number of samples. Is it clear? So KNN is nothing but K nearest neighbor. K is an integer value and it is a hyperparameter. It is a supervised algorithm. It uses labeled data. Training is usually faster, but prediction takes time. So how it identifies its a new sample identifies its own class is that it tries to find the closest K sample to the new sample and then let them vote on an appropriate category. Whichever category has a maximum number of votes, that will become the category of the new sample. This is how the classification is done. It does not have explicit boundaries or it does not create regions or areas. So it has a lot of, it consumes a lot of memory because it has to search the nearest neighbors and also it has to save all the training samples. So if it has a lot of features and if it is not supported by the large number of samples, then it can succumb to the curse of dimensionality. So is it clear? So now we will move on to the next algorithm. This algorithm is called as support vector machines. Most of you would have heard about this one. We will briefly see what this algorithm does. So unlike in KNN, does not find an explicit boundary, but support vector machines finds the explicit boundary between different set of samples. Am I audible?
Yes, ma'am, you're audible, ma'am.
Okay. So support vector machines uses explicit boundary between different set of points. So for the purpose of illustration, we will use 2D data with just two categories. 2D data means what? Dimensionality refers to the features. So 2D means it has only two features and two classes. So let's take one example. We have circles and squares. So if you look at it, it is drawn in two dimensions. So it has two features, X feature and Y feature. And it's a two class problem. These classes are well segregated. So if you want to find a boundary between these two clusters, to keep things simple, we will use a straight line boundary. So we can draw three boundaries like this. Okay. So if you look at it, there are number of lines. I can draw n number of lines which separates the two clusters. But the question is, which line would you choose? All these three lines are separating both the clusters, but which line should we pick up? One way to think about it is to imagine that when a new data comes, how this data will go and fit into it. Suppose, imagine that if any new data is coming, so this new data should combine with any one of these clusters, and this line should facilitate that one. So what will happen? Let us see this individually. So if you have a line like this is number 1, number 2, number 3. So I'm drawing number 1 here.
Just good.
So out of these three boundaries, which one you think is optimal? So we have drawn three lines separating the two clusters. So which one do you think is more optimal? The first one, the second one, or the third one? Any guesses?
Second one.
Second one, ma'am.
Why do you think second one is optimal?
Because there's no bias, no, in both these. One is closer to the square, one is closer to the circle. That's why.
Fantastic, ma'am. So the best line out of the three is the middle one, because it is least likely to make an error if a new point comes. So if a new point comes, it has to, suppose if a new point comes here or comes here, it will drift to one of those clusters. And the other main reason why the second one is good is because it maximizes the separation between the two groups. Unlikely the top and the bottom one, if you look, it is too close to the clusters, so it is possible to misclassify some points. Suppose if a point arrives here, it is likely to be a square, but it can put it into the circle. So there is a possibility of misclassifying the points because they are too close to the clusters, whereas the middle line maximizes the separation between the two groups. So it reduces the chance for misclassification or erroneous classification. So we will select the one line usually which has a maximum separation between the two groups. This algorithm is called the support vector machines. So because SVM finds a line that is farthest from all the points in both the clusters. So if you find out it has a farthest, the distance is larger in the second one, whereas the distance is closer to one thing here and the distance is closer to one thing here. So we will choose the one which maximizes the separation two groups or multiple groups. So why we call it a support vector machine? Machine means you can think it as a synonym for algorithm. It is called as, so instead of saying algorithm, people call it as support vector machines. So let us take another example. So in this example, if you look at the distance between the solid line and the dashed line is called as margin. And the vectors which are flowing through the margin is called as support vectors. So we have three support vectors here. So this vector is again can be thought as a meaning of samples. Instead of saying support samples, we are calling them as support vectors. So the highlighted circles and the highlighted square here are called as support vectors. They define the zone around the center line. So the line passing through that one and the center line, the distance between the center line and the dashed line is called as margin. These dashed lines are defined by the support vectors. So is it clear? So we can rephrase the idea by saying that support vector machine algorithm finds the line with the largest margin. So these are the things you have to remember. So the support vector defines the margin. So suppose, let's assume that we have a new set of data. So here the distinction is very clear. They are well separated, so we can draw the line. Imagine if you have a data point like this, where the separation is, we cannot draw a straight line to separate. What will you do in this case? So in this case, what we will do is that we will have a parameter called C. C is nothing but simply we can call it a C or a clearance parameter. It has a control over the algorithm. What it controls is that it controls how strict the algorithm can let the points into the region between the margins. So if I'm going to draw a margin here, a margin like this, it is allowing some of the points to be within the zone of the margin. So this algorithm will tell us how many points it can let inside or how many points it cannot let inside. So the larger the clearance value, the more the algorithm demands to be in the empty zone. If the smaller is the points, then the more points can be allowed. So let me do it with an example so that it is more clear. So if you look at both, here C is 1E plus 0.5, whereas here C is 0.01. So usually the value of C will tell you how sensitive the points can intrude into the zone. When you have a smaller value of C, you have more points in the zone. When you have a larger value of C, the points are lesser. You have less number of points inside the zone. So lowering the value to C is equal to 0.001 lets you many points to come inside the zone. So as a result of having support vectors to work for this line will fit more horizontally than the previous figure. So if you look at here, this line is more horizontal than this one. So it is letting in more points. So if you what is the implication of having high C and low C is that if you have a high value of C, you are likely to overfit the data. If you have a low value of C,
Underfit.
yeah, you're likely to underfit. Underfitting can take place. So this is a parameter which controls the points in the zone or within the margin. So far it has been so said able to draw a single straight line. Decision boundary is a single straight line. It can separate whether if there are two clusters are far away or close together or overlapping each other. With a straight line, we were able to draw segregate both the things. Imagine if you have a points like this. For example, imagine that you have a point like that, a circle surrounded by a square of circles. So how will you separate these two? So you have a blob of samples of which it is surrounded by a ring of another set of samples. There is no way we can draw a line to separate these two sets. So we have to come up with a clever idea to segregate these things. Any idea how we will separate? Okay, so what we need to do here is that we need to add a third dimension to each point. Imagine that these are the balls kept on a table. So when you keep it on a horizontal table, so it is looking like this. You have kept in a circular fashion. There is no way you can place a line and separate these two. Imagine that you are throwing these balls from the table above. So when you throw the balls, all the balls are in the air, in the same line. So you are throwing the square balls first, and then you throw the circular balls next. So you throw the square object first, and then you throw the circular object secondly. So what will happen is that it will create us two distinct cloud of points. So what you can do, you can place a plane in between. That plane will separate both the things. It is the objects are lying on the table. There is no way you can keep a straight line or a straight ruler to separate these things. So what you will do, you are just throwing those objects in the air in the third dimension. So this is 2D and this is 3D. So you are throwing it in air, you are creating a separation between these two objects. So you can place, still the arrangement has not been changed. Still it is a ring surrounding the circular object. The circular object is still there, but you are pushing this data into a 3D. So we can separate both the objects. Now it is easy to place a plane between them. So line is a linear element in the plane and plane is a linear element in the space. If you want to separate in 2D, you have to place a line. You have to place a plane because it's a linear element in space. So now all the points above the plane are placed into one category. All the points below the plane are placed into another category. So this is how you are separating it. So you can draw the support vectors. So these can be the support vectors of this one. So now that you are placing a plane, you are able to separate in both the categories. So what you can do after this itself, you can transform this one into the 2D. So if you transform this into the 2D, what will happen? So you're mapping these points here. So after you map these points from here, you map the plane also into the 2D. So what you will have is that you will have a clear distinction of it one. So the idea is very simple. So when the objects or when the data points are linearly separable, you place a straight line and then you separate it. SVM works on the linearly separable data. But if you're not able to separate it linearly in a one dimension, what you will do is that you will go to the next dimension, place the data there, separate the data in the next higher dimension, and then map it to the previous dimension. Here in 2D, we are not able to separate it simply. So what we did is that we transform the data into the third dimension, where they are separable, and we place a plane and separate it and then map it back to the 2D. So when we map it back to the 2D, we are able to get the support vectors. Once you get the support vectors, you will be able to draw the decision boundary. Is it clear? So this is what SVM does. So when the data has many dimensions, it is really difficult to distinguish, but distinguish and understand. So we are just limiting ourselves with the 2D one. So it can be hard to decide on the best transformations for improving the clustering. So now I will introduce a term called kernel. So kernel is a mathematical function. So this mathematical function transforms the data into the higher dimensional space. So where it the classes. So SVM works best when the data is linearly separable. Suppose if the data is not linearly separable, then we need to map the data to the higher dimension where it becomes linearly separable. Kernel function will allow us to do this without explicitly transforming the data. So that you call it as a kernel trick. So here what you are doing, so you are not explicitly transforming the data to the 3D, but you are just projecting into the 3D and then finding the separation and then mapping the separation back to the 2D. So the 2D data is not changed. It is not explicitly transformed. Only it was the projection. From the projection, you have learned the separation and you are mapping the projection back. So this is done by the kernel function, and this is called as a kernel trick. So kernel trick is nothing but computing the relationship in the higher dimensional space without explicitly transforming the data. So is it clear? So what we did in SVM is that, so SVM creates an explicit boundary between different set of samples. We saw how to draw a straight line between two clusters, and we learned some of the terminologies involved in the support vector missions. One is margin and other one is support vectors, and the other is the clearance parameter. And then we saw when the data is not linearly separable, how to make it separable using a kernel trick and using the kernel function. So we have seen the gist about SVM. You're not dealing mathematically now. You're just trying to understand the concepts involved in different classifiers. SVM is a non-parametric classifier. It learns directly from the data. It is not learning from the parameter. And also it does not make any assumption about the data. So is it clear? Any questions? If you have no questions, we will go to the next classifier, decision trees.
One doubt I'm having.
Yes.
See, when you're doing in third dimension also, you will be solving it mathematically only, when you're reprojecting it. So why,
Yes,
how does kernel really differentiate that from this? Both are mathematical only,
Yes, ma'am. For the purpose of illustration, I have drawn it in 3D, but we will not be doing in 3D, ma'am.
Okay, so it's only which you will take.
It's only 2D,
Or-
but it will think how it will be in 3D, and then it will draw the projections from the 3D. But that is what I told here. The kernel tree does not compute or what to say, transform the data explicitly. It is just bringing it is what you say is correct. It is just doing mathematically, but for the purpose of illustration, I have drawn it like that, ma'am.
Okay, right. Thanks.
So next we will see about decision trees. So decision tree is also a non-parametric classifier. It is one of the most easy to comprehend. It is most because most of the time we will not know how we arrive at the final conclusion or the result. But this decision trees are more intuitive. They are easy to comprehend. So most of the people, even if they don't get good results, people will go for decision trees because they know how they arrive at the final conclusion. So for that reason, people prefer decision tree, even though its accuracy is low. Like KNN, here also it saves all the samples. It builds a structure around them. That structure is called as a tree. So whenever a new sample comes, it will go through the structure and it will answer quickly. Let's understand this more intuitively. Have anyone played this game 20 questions? So we would have played this in when we are young. So there will be two players. The first player will think about a specific target object. That object can be place, name, or thing. The next player, whom we call the guesser, has to ask 20 questions in an order. That questions should be in yes or no type. So based on the questions, he should narrow down to the target, and if they identify the target within 20 questions, they will win. Otherwise, they will lose. So this game is what to say. It's more fun because it is narrowing.
You're not audible, ma'am.
Ma'am, you're not audible, ma'am.
Okay, am I audible now? So
Yes,
where till what sentence I was audible?
ma'am, till guessing the 20 questions. After that, you are not audible, ma'am.
Okay. So there are two people in the two players. One person has to imagine some object or place or a thing. So the next player is called as a guesser who, with using 20 questions, they have to narrow down. All questions should be or yes or no questions. They have to narrow down to the correct answer. So suppose imagine that first player is asking, the guesser is asking, is this a person? So there can be two answers for us. One is yes, other is no. If the answer is no, it means that the next question will come, is it a place? This also has two answers, yes, no. If the answer is no, then it's obviously a thing. So we can ask, is it made of wood? So here, if it is a person, then we can ask if that person alive. Then if the answer is yes, then we can ask if the person is a male person. If the answer is no, then we can ask if they are your ancestors. So if you look at here, so if it is a place, then we can ask it is on a land. If not, it is on the water. So you are essentially building a tree. So with yes or no, each question has two answers. One is yes or no. So this is the structure of the tree, but this tree is inverted. So each node is split into two, and there is a line which is connecting each node. So this analogy forms the structure of an inverted tree. So the top node is called as root. And the links are called as, or the branches are called as link or branch. And the intermediate nodes are called as internal nodes.
Ma'am, ma'am, you're not audible, ma'am. Ma'am,
Sorry, there was some signal interruption. I will join again.
okay, ma'am.
Am I audible?
Yes, ma'am, you're audible, ma'am.
Yeah. So to restate this, this is a structure of an inverted tree. So we can, instead of inverted tree, we call this structure as tree. So the starting node is called as a root node, and the link which connects the two nodes is called as a link or a branch. The intermediate nodes are called as internal nodes or decision nodes. And the one which ends is called as leaves. So a tree can be symmetrical or unsymmetrical. So if they are symmetrical, if the tree is a symmetrical tree, we call it as balanced. If they are unsymmetrical, we call it as unbalanced. So in practice, most of the trees are unbalanced because they are, so what we can do is that we can run some algorithms to make it balanced. For based on the particular application, we can make it as balanced or unbalanced. So next, suppose imagine we have a tree like this. So leaf I'm drawing with a square. So the nodes are drawn with the circle and the leaves are drawn with the square. So this is the root node. The depth of the root node is 0. The depth of the first node immediately below the root node is 1. The depth of this node is 2. The depth of this node is 3. So the depth of this leaf is 4. So you can say that tree or the tree depth is 4 here. So this is a node and this is an edge. Edge, link or branch, you can call it as anything. So the another terminology to be remembered is the depth of the tree. Here the depth is 4. You start with the root, you assign 0 depth to the root, and for every node you provide 1 depth, add 1 depth, and that will lead to the final depth. So every node except the root node has a parent. For example, for this leaf, this node is a parent. For this node is a parent. For this node is a parent. Except for the root, every node has a parent except for the root node, every node has a parent. So the node which is immediately following the node is called as a children. So this node is a child of this node is a child of this one, this node is a child of this, and this is a child of this one. So there are two types of child. One is the immediate children. The other one is the distant children. So immediate children means the children that are directly connected to the parent are called as immediate children. The children which are connected through the sequence of another node is called as distant children. So if you see, this is a children of this. So this is a child of this one. Whereas this is a distant children of this. So it is a distant children of this one. So is it clear?
Could you indicate in the thing diagram? I couldn't able to see them.
Mark, laser pointer is not working, Dr. Pratibha.
Okay, ma'am. So let us understand the terminologies correctly. Is it clear? Is it visible now?
Now it's working.
So this is a root node. So the root node has a depth 0, and this is the depth 1. The node which is immediately following the root is called as depth 1, and this is depth 2, this is depth 3, this is depth 4. So the depth of the tree or the height of the tree is 4 here. So there are so we call it a, there is a relationship just like a family tree. Here also in the tree we have the relationship called as parent and children. So if the, what to say, every node except the root node has a parent. For example, for these leaves, this is a parent. For this this node, this is a parent. For this node, this is a parent. Then if you look at, this is the child of this node. This is a child of this node. This is the child of this node. And we can also have two types of children. One is immediate children and other one is distant children. Immediate children means for this node 3, this is the immediate children. For this one, this is the immediate children. For this one, this is an immediate children. Whereas for this one, these are distant children of 2. Is it understandable now? So immediate children means they are directly connected to the parent. If they are connected through a sequence of nodes, then they are called as distant children. So this is an immediate children of, so maybe I will write here. So these two are the immediate children of this node. But they are distant children of this node because they are connected through a sequence of nodes here. Is it clear now?
Yes.
Okay. So we can focus our attention on a specific node. Suppose if you take this specific node, this is a parent node. This parent has 2 children, 2 immediate children. It has 1, 2, 3, 4, 5, 6. It has 6 distant children. So if you take this as a parent, it has 2 immediate children. It has 6 distant children. Likewise, and it has one parent, which is this node. So you can consider this node. You can draw a subtree out of this node. So its children and distant children together will form a subtree. So this complete thing is a tree. But if you consider a specific node along with its children's and distant children's, they form a subtree. So this is a subtree. Is it clear? And there is one more terminology. So parents of, children of the same parent are called as siblings. So now it is very interesting that the 20 questions of the tree is a binary thing. So every parent has exactly 2 children, either yes or no. If you look at here, it is either yes or no questions. So either it is yes or no question. So it has, it is a binary. So every node has a binary question. So it was easy to draw. So sometimes what will happen is that we will have more than 2 options. Suppose if you are guessing a birthday of somebody. So we can have whether it is in January, whether it is in February, whether it is in March, or it is in another month. So if you look at here, you are guessing a birthday of somebody. So you have these many options. So this one you can have yes or no for that one, whether it is in February, whether it is in March. So I can call this tree as a bushy tree. When it has more than binary options, when it has more number of options, you call this tree as a bush. It has a many bushes, so you call it as a bush. It is possible to convert this bushy tree into a binary tree. How the binary tree means? January, you can have yes or no. So if it is no, then you go to February. Then you ask a question whether the birthday month is in February or not. Then you can go to March. Likewise, you can convert a bushy tree into a binary tree. It is possible to convert a bushy tree into a bushy tree and binary tree. Clear? So we can go back and forth. We can draw trees, however, in whatever format we want. We can draw it in a clear and a concise form. To have, based on the discussion at hand, we can draw a clear and a concise diagram. We can convert a bushy tree into a binary. We can convert binary into a bushy tree based on our application. So generally, these decision trees has a general idea to categorize data. So we have 2 types of decision tree. So if you are categorizing categorical data, then you call it as Categorical variable decision tree. Suppose if you want to distinguish continuous variables as in regression problems, you call them as continuous variable decision trees. So the general idea is that you build a tree during the training, you assign roots and the parent node, and then based on the features of the sample, you assign the nodes, and then the leaf node will contain all the training samples. We will see with an example right now. Suppose you are traversing a tree and it has both circles and squares in it. So you can ask a question, this is a leaf. You can ask a question at the leaf, whether is it more circles than a square. If the answer is yes, then you can put the training data into circles. If the answer is no, then you put the training samples into a square. So what you're doing essentially here is that you're taking a leaf, replacing it with a node and two leaves. So you are splitting a node, you are splitting a leaf, and then you are coming up with the feature. So if you look at here, every node has a question, whether it is a place, whether it is alive. So you start from the root node and you test the features of the sample using the test available under each node. So what you can do here is that these questions can take the data from one feature or from all the features, aggregate of all the features. It is depending on it. So it is not necessary that we need to test all the features in one single node. You can just test one feature, or you can test multiple features and then take the aggregate as an answer. So we can split the node in whatever form we want. So here what we have done, we have taken the leaf and we have replaced it with one node and two leaves. So the roots will have the So the roots and the nodes will have the test questions between them, and they can test the features, and the leaf nodes will contain the training samples at the end. Based on the classification, they will have the training samples. As in here, if you look at all the male training samples will come here. All the ancestors will come here. Whether it is made of wood or things, all the things decision tree. Once we are done with the training, we will evaluate a new sample. It is very easy to evaluate. We just start at the root, work our way down to the tree, following the branches on the samples. So then when we apply it to the features, we test it at each node. Then finally, when we land on the tree, we report whether it belongs to that particular category of the object of the tree or leaf or not. So in practice, if you look at it, the test can be very imperfect. It can contain mixture of objects like this. But what we can do is that in order to improve the efficiency, we can limit the number of nodes which is present in the tree. So there is no global strategy to find the smallest number of trees or to find the efficient tree. We just split the nodes on the fly just by using the information we have at our hand. So this is how we create the decision trees. Any questions?
So this can be used as both as a classifier as a regression model, ma'am.
Yeah, we can use that is what we're doing. If you are using in regression, we use continuous variable decision trees. If we are using it as a classifier, then use categorical variable decision tree.
Okay.
So it can be used in both the purposes.
Okay. Thank you.
So now we will see how to build a tree. Imagine that we have two data set, two set of clusters. 1 to the square and 1.
You're not audible, ma'am.
Sorry, there was a continuous signal disruption. Am I audible now? Is my page visible?
Yes. Yes.
So let's see an example for building the tree. Imagine that you have a set of data like this. So you have two clusters of data which are clearly separated. They represent two classes. So suppose if you have only 2 leaves, then you can get a separation like this. So with 2 leaves, just 2 leaves, your separation is like this. But it is still not a well separated data. So what you do, you can try to increase the number. With 3 leaves, you can have something like this. With 7 leaves, you get a separation like this. So as you increase the number of leaves, what happens is that it is gradually getting separated. So if the 7 leaves are better than 2 leaves. 2 leaves is separating into 2 halves. 7 leaves is also separating into 2 halves, but you get a better, better split in both vertically and in horizontal direction using 7 number of leaves. So this is just by trial and error. We will understand with asking more number of questions and asking more number of, with having more number of nodes and leaves, you will able to find an optimal solution for your this one, because decision trees are so sensitive to each input data. And also one more point is that this decision trees are always overfit the data, because every training sample influences the tree shape. So it is most likely to overfit the data. So what we can do is that sometimes, suppose if you are using for one algorithm, you got a split like this. Suppose if I'm using another algorithm, not another algorithm, if I'm using the same experiment with a different set of data, I can get a split like this. So if I randomly pick different set of data for this one, and this one is for a different set of data from the same training set, you might end up getting two different separations. Both are identical, both are similar, but they are not identical. So they are likely to overfit the data. So this is a problem which we face in decision trees, but nevertheless, since it is more comprehensive to understand, people use decision trees. And another important concept which we need to understand is about how to split the nodes, splitting the nodes. So we have many libraries to split the algorithm, split the nodes. The first question we should ask is that, does it need to be split? If you come across a node, we need to ask whether we need to split the node or not. Second question is how to split the node. So it is based on two processes. The first thing is that we will see the purity of the nodes. Suppose if the nodes have training data from same category, then you call the node to be pure. If it is from multiple category, then you call it as impure. So what you will do is that first you will take a node to decide whether we need to split or not. You will identify the purity of the node. So once you know the purity of the node, whether it is you fix a threshold and you compare the purity against the threshold. If the node is too impure by comparing the threshold, then what you will do, you will split the node. If the node has highest purity, you don't split the node. So that is how you decide whether to split the node or not. So there are two ways to check the quality of the split. So the first one is called as information gain. So what we will do in information gain is that we will check the entropy of all the children. Entropy of all the children will be calculated. So what is entropy? Entropy is a measure of complexity. What we learned is that entropy is a measure of information or a measure of uncertainty. So here we can consider this as a measure of complexity. So what we will do is that we will compare the entropy of all the children of node, add them together, and then compare it with the parent cell. So if the cell is pure, then we will have low entropy, low complexity if it is pure. So we will have the entropy value will be very high. So this is how you understand the quality of the split. So the second way to understand, evaluate the splitting test is through Gini impurity. So what we will do in Gini impurity is that it is a technique which is designed to minimize the probability of misclassification of a sample. Suppose, for example, if a leaf has 10 samples of category A and 90 samples of category B, if a new sample comes, if a new sample is coming, and then we can report it belongs to category A, there would be 10% chance of that we are wrong. So what the Gini impurity does is that it measures those errors at each leaf. At each leaf, what it will do, it will calculate the error. And after trying multiple split, it will tabulate all the errors. For every split, it will calculate the error. And then it will tabulate all the error and find the error which has a, and it will find whichever has a least error, it will find that split and implement that one. So what Gini impurity does is that it tries multiple splits. For each split, it calculates the error. And finally, the one with the least error will be chosen for the classification process. So this is how Gini impurity is done to minimize the probability of misclassification. So this is how it implements. So there are two ways of checking the quality of the split. One is information gain, where it uses the entropy to check the purity of it. And the second one is Gini impurity. It tries to reduce the probability of misclassification by checking the error of multiple splits. So this is how splitting of the nodes are done. So is it clear? So in the decision tree, what we saw is that we saw some of the terminology. Decision tree is a non-parametric classifier. It learns directly from the data. It is more useful because it helps us to comprehend well. So we learned the different terminologies involved in the tree, and then how we also learned the distinction difference between the bushy tree and the binary tree, and then we learned how to split a node, and we also see how to build a tree, and we also saw how the splitting of the nodes are done with using two techniques. Splitting of the nodes is done. Any questions? If you have no questions, in the next class, we will see one example for a, so far we have seen in this class, we have seen 3 examples of non-parametric classifier. In the next class, we will see about parametric classifier. There is only one downfall in the decision tree, that is it has a lot of overfitting. So that is the problem with this one. To avoid the problem of overfitting, what we can do is that there is one technique called pruning or trimming of the leaves. So what we will do is that we will limit the number of trees, or else we will allow the tree to grow and then we will chop off the nodes and trees. So this is how we will overcome overfitting. So is it clear? So if you have no questions, we will meet in the next class. Thank you.
Thank you, ma'am.